Welcome to the pre-recording of the second half of Lecture 9, scheduled for the start of the fourth week in this 8-week summer course on computer algorithms. We introduced divide and conquer in the previous lecture, and in the Lecture 9, we are giving two applications of divide and conquer. So this course has its focus on discrete algorithms, although as you can see from the slides, we have derived in the first half of Lecture 9 the fast Fourier transform, a very important method in science and engineering, which runs in subquadratic or quasi-linear time. So if you are multiplying two polynomials, the straightforward method gives you a quadratic time. Divide and conquer gives you a subquadratic time. So that was done in the first half. In the second half of this lecture, we're going to reduce from cubic time, the straightforward algorithm, to multiply two matrices of size n. We're going to reduce this to n to some power that lies between 2 and 3. So that's the subcubic time. For that, we need the master method to solve recurrences. And this is where we are going to start. But let me first go to the problem. We are multiplying matrices, and we're going to look at a recursive matrix multiplication. So divide and conquer consists in partitioning a big problem into smaller ones, solve the smaller ones, and then combine the solutions of the smaller problems to the big problem. Seems a lot of work, but it will pay off. So here for the problem of matrix multiplication, we take one product of matrices of size n, and we reduce this to multiplications of size n by 2, n over 2. So how do we do this? Well, we partition each matrix in 4 blocks or 4 tiles of size n over 2. So we have now, instead of one big matrix of size n on input, the matrix A, we have 4 submatrices, A11, A12, A21, A22. We have 4 submatrices that partition the second matrix. And the result C can then be computed via 8 multiplications of half the size and 4 additions, as is shown here in this product. Okay, how does this go recursively? If we are defining a recursive algorithm, we must know when to stop. The base case is when the size of the matrix is 1. Then you just have to multiply two numbers. And that runs in constant time. So we are interested here not in actual computing matrices by matrices, but we are interested in the running time. So we ended the first part of lecture 9 with a referral to linear algebra. Here actually we are doing linear algebra, but with a focus on the running time. So the combination step, after having done all the multiplications of matrices of half the size, consists in the 4 additions. Adding n by n matrices takes time n squared. We have to go through all the rows, and every row contains n elements. So adding everything up, doing this 4 times, is big data of n squared. So for most of this course, we have been interested in worst case upper bounds. But here we will get very precise bounds. So the big data again means that you cannot do it in less time than a constant times n square. But you also do not need to do more than n square time. So also a constant times n square. So it is a very tight upper bound. And the constants will depend on the estimates that you have for the elementary operations, upper bounds, lower bounds. Okay, so the bottom line of this slide is that we have derived the recurrence that states that the time to multiply two matrices of times n equals, so we are having tight upper bounds, equals 8 multiplications of size n over 2. So therefore the time is 8 times the time it takes to multiply matrices of half the size. And the combination step, the addition of all the matrices, takes time big data n square. Okay, how do we resolve this now? Well, we have to apply what is called the master theorem. So the master theorem deals with recursions of this type. So there are three ingredients there. So we have the little a, which defines the number of sub-problems you have. The little b defines the division factor, so the reduction factor by which you reduce the size. So typically this is cut in half. B is a typical value too. And then we have the costs of the um, combination, and typically this is a constant times a monomial in n. So like in the um, matrix multiplication, we have a function that is quadratic in n. So this is the input. So it is a theorem, but you could see this as a method that gives you a formula. You give in two parameters, a and b, and another expression in n, and then it's going to give you a big data bound. So we have started with merge sort as kind of the prototype divide and conquer method of to sort numbers. Merge sort is covered by the second case here. So I will first focus on the second case where we in merge sort we cut in two, so b is 2, so we are looking at two logarithms, and we have two halves. So both a and b are 2. The 2 logarithm of 2 is 1. So we are going to end up with um, a time that is linear in n times a logarithmic factor, provided that our combination step is also linear. So this is how one can read this second line here. We are going to interpret this. So I'm giving numerical interpretations for a and b both be equal to 2. Common factors in merge sort, where also the merge is big data of n. So we run through all the elements again to construct the sorted sequence. The first and the third case are when the combination time requires less in the first case or requires more in the second case. So what do we have in the first case? We may end up with a linear time algorithm. In the second case, in a linear time algorithm, or some power. I'm saying now linear if a and b are both the same. We may end up if we have an extra condition here, we may end up at an algorithm where the cost is proportional to this f. Okay, so these are the three cases. The middle case is a case that we can interpret. Here is the interpretation again. So this is how the unrolling works for merge sort. Two equal halves where we cut the size evenly. So this is the 2, and we have 2 of them. So here you see that in this specific case, which is the most simplest case, so you could also have 2 here, 4 here, 4 there, where the workload, so you see the load in the children here, you have C of n at the root. If you add up the work done by the children at the children nodes, then actually you have the same C times n. If you would do this again at, suppose that your height of the tree, the depth of the tree is just 2, then you would find again 4 times the C of n. In the two other cases, either your total cost is dominated by the leaves. So actually the reduction time is very straightforward. Could also be a constant. Or it is dominated by the root. So actually when you come back from your solving of the sub-problems, you have to do more and more work. So let's look at these two cases. So again, we have the middle case that was sitting here. How do we interpret this now in terms of this L? The big L here is determined by the depth of the tree. So in general, the B is the factor by which we cut the size of the problems. So that also is going to determine, together with this number of subproblems, how many leaves you have. So you can see that the depth of the tree will depend on the logarithm, if you have a 2 logarithm by default. But if the A grows, you will have more and more leaves. So if your function that governs the combination stage grows at the same level as, same rate as the number of leaves, then you will have the n to that power, where you actually have the big data is actually the big data of the number of leaves. Now you could have that it is bounded or that it grows at least as fast. So you have to release the big data. Either you still have an upper bound, could be less, or you have a lower bound. So if we relate the combination cost to the size of the tree, in particular the number of leaves, we see that actually the running time depends on the number of leaves. Okay, the second case is here for well examined. We have now this cost that has this logarithmic factor, but you still have this little a. If the little a is 2, then you have n log n, but the little a may be more. So you may have also a quadratic factor there. So we will not prove the theorem, but there are graduate students in this course, so at least you should know where the proof can be found. I should also have pointed out that this book, so we follow the book of Kleinberg and Tardos. The reference that is mentioned here also treats the fast Fourier transform quite well. So that's also another way to read about an alternative um, source for the algorithms that we consider in this course. All right, going back to our merge sort. So in some sense, this is merge sort again. We have done this already. Actually, we did it twice prior to this lecture. But now with the master method, we have a sharp upper bound. So we have the big data. So, and actually, I should have emphasized this. We are interested in the big O, but we actually do have the big data n log 2 of n. So I illustrated this already. Here is now the problem that we are interested in. So I'm 15 minutes in this course. In this second pre-recording for lecture 9. And we derive the obvious. So multiplication in the straightforward way is cubic in n. So we knew this already. But here again, we have the big data. Should have emphasized this. I will correct this still. But doing this recursively, so the bottom line of the application of this theorem here of the master method with b remains 2, so we cut our problems in half, but we have, instead of 2 of them, we have 8 of them. What is also problematic is that we are in the first case, where actually the recombination cost is quadratic. So the number of additions that we had to do to formulate the submatrices in the product. Okay, first part ends with an exercise. So apply the master method to find the tight asymptotic bound on this recurrence, where you have the combination step that runs in time 1 over half. Do you have a logarithmic cost? Perhaps. Notice that you have only 2 subproblems, but the sizes are cut in 4. Strassen's method is a recursive method to multiply 2 matrices that will run in subcubic time. Okay, let's first define Strassen's method. So we have the partitioning as before. And now we make 10 submatrices, S1 to S10, and they involve either a subtraction or an addition of matrices. Seems a lot of work, and again, this will only be valid if your n is at least 10, but n should be a lot larger. So these are asymptotic costs. So the algorithms here will not yield anything if the n is too small. So here we have the definition of all these sub steps. So this will be the time it takes to subdivide, and it will be the time when you have to add in your recurrence. It's a big data of n square. Nothing gained so far, but now consider the making of the product. The key part is, we will go very carefully through the correctness, is that instead of 8 matrix multiplications of matrices half the size, we have 7 of them. We have 7 products where we multiply the blocks of A with blocks of B and those submatrices S1 to S10. So you can see that actually it looks as if we did not need all submatrices, but it's not true. We actually need all 10 of them. Here it is spelled out again what these products are in terms of the original blocked matrices of the input. So these are well defined. Then there is another construction step. So we had already the 10 steps to make the submatrices. We need then, here you see, to formulate the 4 submatrices in the product. We need 4 additions, actually 5 additions and 3 subtractions, which is again big theta of n square. So this is absorbed in the big theta of this f of n that when we will apply the master method. Okay, it's not at all obvious that this is a algorithm to compute the matrix problem product correctly. So we will go carefully through now there is 4 steps in the correctness proof. Okay, let's first do the easiest part. So the submatrix C11 is computed by two products of matrices half the size. And then we add those twos up. And you can see by the definition, the straightforward definition of C12 is that indeed we obtain the formula that defines 1, 2, the submatrix 1, 2 of the product. If you just add up these two, then the cross term actually disappears. So this is a correct computation of that part of the product. Similar for the symmetry, the submatrix to 1 in the product follows the same logic by adding the matrices P3 and B4 obtained by 2 matrix multiplications of half the size. So here is actually what they represent. So if we know what they represent, then we see that their addition causes a term to cancel. And indeed, we have the proper cross products, as agrees with the definition of this submatrix. The other two cases are a little bit more complicated, but not that much. So we have the first block, C11, which is defined by this sum, and then we subtract also. We have 2 additions and 1 subtraction. If we spell out what the terms in the sum for C11 means, then we can see again with direct verification that C11 in the product is actually what we compute. So we compute what we represent here corresponds to the definition of C11. Direct verification. Also for C22 direct verification, we actually obtain the definition of C22. So it's a little bit tedious, but you can see by the direct verification arranges the terms. So we have the term for P5. If we then write underneath it the definition of P1, we see that one term cancels out. The extra term introduced by P1 is cancelled out by P7. And to complete this puzzle with the third line, we can actually see that the pluses cancel out with the minuses, and we obtain the 2 terms that also appear in the definition of the product indexed by 2, 2 in this matrix. Okay, we have a correct method. It's a complicated method, but did our efforts now actually pay off? Do we have a more efficient method than the classical straightforward matrix multiplication? We do, and this is where our attention to the master method pays off. What do we have? We have a recurrence stated here so this contains the essence of the recurrence. The base case is 1 again, and we have to do 7 matrix multiplications of half the size. The computation of the submatrices involves 10 additions or subtractions. We also have the recombination of the product, which is also involving many additions and subtractions, but the numbers are constant. Okay, we apply the master method, where here we have that the combination is less than this n to the power the 2 log of 7. So why is that? Because the 2 log of 7, so here it is 2 to the power 8, and the 2 to the power 8, 2.8, n to the 2.8 is less than 2. So we are in the first case of the master method. If you like the epsilon, it's not an epsilon in the sense that it is an infinitesimal, it's actually quite large, 0.8. So we do have that this exponent also then shows up in the final running time. So we have a subcubic running time that is not cubic. The exponent 2.8 is less than 3, but larger than 2. It's also actually not quadratic. Okay, in this presentation, perhaps I went a little bit too fast because there was a lot of repetition. So you should actually take it a little bit on faith. So I would strongly encourage that you go slower through this recording. In this presentation, I followed section 4.2 of the Introduction to Algorithms book. So this is not the textbook that we selected for this course, the Kleinberg-Dardos book, but it is a different book. So Strassen's method is a very good application of the divide and conquer that was extensively covered in the chapter that we are going to conclude in the textbook. So I will conclude with a listing of the exercises that will be collected at the end of the 4th week in this 8-week summer course.